Hey there, I am here to review with you the first learning goal for your upcoming thermochemistry unit test. The first learning goal is all about the energy and how it flows in a reaction, and then also kind of how it appears on a potential energy diagram. Okay, so let's start by just kind of reviewing some major topics that I need to make sure you remember. And that first idea I need you to remember is that all chemical reactions involve energy, right? When a reaction happens, the first thing that has to occur is the molecules have to have their bonds broken, and it takes energy to do that. So a chemical reaction has to absorb energy to break bonds. Then once the molecules all come slamming back together, and it happens very fast, the energy then that was absorbed to break those bonds is released. So energy is released. So every single chemical reaction involves the absorption and the release of energy. Okay, now a little side note about that energy. You may be asked a question along the lines of where do you find energy? And the answer to that is in the bonds, right? Remember that a bond is not actually like a physical thing. It's not like a stick that holds two atoms together. It is a force of attraction or actual energy that holds things together. Okay, so the other thing I want you to remember is that when molecules aren't reacting, the energy is found within the bonds. Okay. Now, the type of reaction, whether or not a reaction is exo or endothermic, is based entirely on that energy and what happens overall. So every reaction involves the absorption and release of energy. If the absorption is more than the release, then it's one kind, and if it's vice versa, then it's the other kind. Okay, so let's talk about the two right now. So for an exothermic reaction, remember what the prefix exo means? It sounds kind of like exiting. So this would be energy leaving. So if energy is leaving, that means that more energy is released, right? Whereas an endothermic reaction, I think that sounds like into, right? So in this case, more energy is absorbed than released, okay? A couple of other things I want you to remember, and you will definitely have test questions about, is that when you write an equation involving energy, for an exothermic reaction, the energy should be placed on the product side because overall there's more energy produced, and that'll make more sense when we look at a picture here in a second, than there is absorbed. And also notice that the total change in energy, or the value given to the energy, is a negative number. That negative represents a loss, okay? Again, the opposite of that is endothermic. Endothermic energy is considered a reactant because more energy is put in overall than is actually released. And it would have a positive value because it's a gain. Okay, so let's check out some potential energy diagrams. You will have to answer some questions about a potential energy diagram, like, for example, be able to label the reactants and the products, identify the type of reaction from the potential energy diagram, all that fun stuff. So I'm going to just give one a draw here. I'm pretty sure my dog is throwing up, so that's terrible. Get off the chair. Okay. Anyway, sorry. So you have time passing for a reaction. Oh my goodness gracious. And then you have potential energy on the y-axis, right? So that's the potential energy. So we have where the reaction starts, right? Then you're going to have energy absorbed. And remember, the point of that energy is being absorbed to break the bonds. And you're going to get up here to what we call the top of the hill. What you have up here are just a bunch of atoms that are super reactive. It's called the activated complex. They're not happy in that state because they have all this extra energy absorbed. And what they're going to do is they're going to start releasing that energy. And then as they release that energy, they're going to come slamming back together in new combinations. Now, if they end up lower than where they started, in other words, this hill is bigger than the initial hill, more energy is released, and this would be considered an exothermic reaction. This is exothermic, right? There is more energy released. And let's just label a couple of features on this. So first of all, that hill that I mentioned, and people really do call it a hill, so you probably see that, like if you looked it up, that represents our activation energy. Okay. And of course, since this is where we started our reaction, these are our reactants, and that makes these our products. Okay. So this is a potential energy diagram for an exothermic reaction. The other thing that I want you to keep in mind is that what we want to really compare is the difference between these two values, right? This value, this right here, this difference. This is what we call our delta H, our change in energy. And remember that delta H is equal to the products minus the reactants. Okay, and since this is a small number in this case, right, it's smaller, and this is a big number, that's going to give us a delta H with a negative value. Okay, so that's why we say that an exothermic reaction has a negative value. You can actually put new numbers to that. Okay, so that's a potential energy diagram for an exothermic reaction. So let's check out an endothermic reaction now. Another piece of paper. We'll do the same thing. We'll draw our potential energy diagram. Okay, so we start with our reactants. We have our hill, so the energy is absorbed. Again, we're breaking all those bonds. We form the activation complex, and then they come slamming back together to form new products. In an endothermic reaction, notice that the products are formed when much less energy is released, right? So this is endothermic. Okay, and we have more energy is absorbed if we were to look at those two values, right? So again, here's our reactants. Here's our products, okay? This hill right here is our activation energy. All right, and the difference from here to here, right, from this line to this line, that would be our delta H. That's the change in energy overall, okay? And again, so if we write that out, our delta H is equal to the products minus the reactants. Hopefully you guys don't mind my abbreviations, but I think that makes this a little bit easier. And this time the product is a big number and the reactants are smaller, right? So our delta H is going to be a positive number. So whenever you see energy that's positive, that tells you that it is an endothermic reaction and that energy had to be gained. In all honesty, most reactions release energy. Most reactions are exothermic. There's certainly lots of exceptions, but most of them are endothermic. Okay. Last thing that you need to understand for the test that you will definitely have questions on is the idea of a catalyst. Okay. So, these reactions all require energy in order to happen, but sometimes that energy isn't available. Like, for example, in life, you are the result of all these incredible chemical reactions that won't happen on their own. Like, it requires way more energy. And so like your body temperature would have to be in the thousands instead of just 98. And it requires thousands of years, which of course we don't live that long. And so why do our chemical reactions still occur? That is because we are full of chemicals called catalysts, specifically enzymes, when we're talking about life. And what a catalyst does, here I'll kind of draw it on here, is a catalyst comes in and it actually literally envelops the molecules and it drops the activation energy. So less energy is required in order for the reaction to occur, okay? So this line right here represents a catalyst. And you can see that there's less activation energy needed. But the other thing that I really want you to point out, and this is, I think, a more important idea, is that the reactants and the products have not changed. So the change in delta H is still going to be the same. So if you just had numbers in front of you, you wouldn't be able to tell if a catalyst was involved. You'd have to be given a potential energy diagram and look at it from there, okay? But you'll definitely be asked a question about that, whether or not a catalyst affects a reaction. And the answer is that it lowers the activation energy, but does not change the reactants or products, okay? I think that's all that you need to know for this particular section. If you are doing your review after you check your answers, and you still have a question, please make sure that you reach out to me ASAP. All right. Now's the awkward part where I figure out how to turn it off.